Good evening. My goal here this evening is to, on April 9th, 2017, is to talk a little more about Quadrays and how to integrate this coordinate system with this coordinate system. For shorthand, we can call this Earthling math, Martian math, or if you'd prefer XYZ math, IVM math. Now, what do we mean by the IVM, isotropic vector matrix? Same thing as the octet truss. The thing about Quadrays is they came into the world through multiple people, and so did Quadrays. So did the IVM actually. Quadrays and the IVM were in the wind, I would say. And so I heard about them on a listserv called Synergetics L from David Chaco, and I got the ball rolling on that listserv, and we did a lot of development together. But from my point of view, that's where I learned about them. But then Daryl Jarmusch was in contact, and he clearly had the same kind of thing going on his own. So we say he invented them or David invented them. When you're starved for credit, people are fighting for priority, then this kind of thing becomes kind of competitive. I think back to Fibonacci's day in Pisa when they weren't Italians yet. Italy was not a nation yet, but the peninsula of Italy, let's go there. Mathematicians would compete publicly. It was kind of like a tournament. It was like a game show today to solve polynomials. Who could do it quicker? To a polynomial to the third degree. If you remember from high school, polynomials to the second degree are somewhat easy to solve with a few steps, but as you go up to the third degree, even to the fourth degree, that starts to be pretty challenging. Nevertheless, that was a basis upon which fame was obtained. You could get a patron, perhaps, if you were the best one in that kind of cockfight between mathematicians. So that kind of scarcity pervades in our world, and we worry about who's going to get credit. So I wanted to make an analogy with the octet truss. Kind of crazily, you might think, how do you get a patent on something so eternal as the isotropic vector matrix? Like, could Descartes have patented the XYZ coordinate system? Well, in terms of coordinate system, maybe not. But in terms of a practical way to bring 12 rods together, they're not going to magically just stick together. You have to have some kind of system. You have to have some kind of invention. And that's what Fuller patented, was some particular way of doing the isotropic vector matrix. And that means future patents along the same lines have to cite his. It's kind of a whole other database of citations outside of scholarly writing. You've got the whole patent database, which Google is nicely organized now. But let's just remember, here's my point, Alexander Graham Bell, at the turn of the century, from 1800 to 1900, about 1907 onwards, he's doing these amazing, this is by Dorothy Harley Eber, and there's a prologue here by Buckminster Fuller. This book is called Genius at Work, Images of Alexander Graham Bell. And he called these things kites. I believe the Smithsonian Museum has some examples. See if I can quickly find a picture of that tower, an amazing high tower. So great minds think alike, and it's kind of reassuring actually that if the isotropic vector matrix really is as important as Fuller thought it was, that someone else besides him would have found it fascinating. Here's that tower. So with the benefit of hindsight, looking back, we can see, a mathematician named Somerville was working on space-filling tetrahedra around the same time Fuller was, maybe earlier, but did they know each other? I don't know, actually. Fuller was not aware of Bell's work until much later, and he was like you and I probably. It's like I just thought he invented the telephone. So again, ideas seep in, and we all get to contribute. That's what open source is all about. So I have these open source assets that I'm now going to talk about to help you get up to speed and join the fun. Contribute to this emerging little branch of mathematics, another little coordinate system, Quadrays. We're going to take this caltrop and orient it vis-a-vis this cube in a specific way. Now, how accurate are the calculations? They're algebraically accurate. However, I'm in the middle of converting from floating point to a mixture of floating point and extended precision. So some of the numbers are going to just be floating point accuracy. And that brings me to another point. Fuller is probably famous for saying nature is not using pi. And what does he mean by that? Or phi, or any of these numbers with unresolved decimal expansions. Why? Because conceptually, metaphysically, I think Fuller would say, we have access to algorithms that will spit these digits out indefinitely, but do we have any evidence that energy is computing in that way, other than outside our computers when soap bubbles form or ocean bubbles form in the wake of a ship? Is pi being computed to trillions of places? Do we have physical phenomena that is that small, that we could have that many significant digits? And we don't. We don't have the instrumentation, nor do we really have a basis for saying phenomena, energetic phenomena, have to live up to our conceptual idea of perfection. Really what we have is less perfect because it doesn't exist energetically. That which actually has spatial temporal existence has some added ability or capability that just conceptually we don't have. We can't just create it out of nothing. It has to be created out of energy. So anyway, giving respect to nature for however it does circles, it may not be involving pi the way we think of pi. Now that's a philosophical kind of position or statement, and that's why I would say we should treat synergetics more as a philosophy, not just it's not a physics or a math, it's something in between. So let's look at Quadrays. I've already been running this as a test, trying to get this to work properly for tonight's little investigation. I'm just going to suggest a way of getting started. Instead of using the unit edge of 1 or 2 as I'm using in this picture, or as Bucky was using, and assuming D being 2, let's have D be 1. So 1 to the third power, as we envision third powering in synergetics, is this tetrahedron on the left there. So that's going to be our unit volume in synergetics, and on the right, the R equals 0.5 or 1/2. And that would be the unit cube. And their volumes are not quite the same. As we went over, the unit cube is a little bit bigger than the unit tetrahedron. But I can call them both unit because I'm going back and forth. Remember the synergetics constant and so forth. So with the caltrop, how do we want to orient it vis-a-vis this cube with now D equal 1? We've decided to make D equal 1 instead of 2. So the whole cube is, now we can think of the R units as being square root of 2 over 2, whereas before they were just square root of 2. The unit cube has a body diagonal from corner to totally opposite corner through the center of the cube. The unit cube has square root of 3 for that. However, because our edges are all square root of 2 over 2, the square root of 2 over 2 is like a scale factor. And so the actual body diagonal of this cube now is going to be square root of 3 times square root of 2 over 2. So that's what I'm computing further down on line 16 and 17 in this script. I'm just looking ahead and getting my corner to cube center length, so half of the body diagonal. What's that going to be? It's going to be half of the square root of 3 times the scale factor of square root of 2 over 2. That's what I want the length of each of my quadrays to be, because I want my quadrays to define an encompassing or embracing tetrahedron, where all the edges are 1. So this will be unit volume in Synergetics. So what I'm going to be doing in this script is creating a Q vector or a quadray using my open source software, and then creating the B and the C as well, giving me 3 vectors to the corners of one quadrant face. So it doesn't matter which quadrant, they're all going to have a volume of what? 1/4, because this is an IVM volume of 1/4, because this is our unit volume tetrahedron. So I'm expecting when I print out the IVM volume of that tetrahedron made of 3 quadrays from the center, I expect that quadrant to have a volume of 1/4, 0.25. So those are my expectations. And finally, I'm just going to confirm that this is scaled properly now. I'm going to take the X, Y, and Z vectors, just normal vectors now, not quadrays. Just take some ordinary vectors of length 0.5, like in the picture, and confirm that the volume of the cube is what we expect, unit volume in XYZ volume. So I'm going to print that out. However, I have to multiply by 6, because once I get this tetrahedron, once I get X, Y, and Z, it's not going to give me the cube. My function called maketet, I should explain that actually. Maketet takes any 3 edges coming off a common vertex or apex. Any 3 edges, doesn't matter about angles. And then it computes what the remaining 3 edges would have to be in terms of length. And then it feeds all 6 lengths, the 3 you gave it and the 3 that are determined thereby, into a method of the tetrahedron class inside of my tetravolume module. It's pretty much the whole purpose of this tetrahedron class is to munch through a method for computing volume based on edge lengths only. And I credit Gerald de Jong for tweaking things that Euler did. He derived on his own, having been inspired by Euler. He can tell the story to come up with this code. This is some of the stuff we did on Synergetics L back when quadrays were still fresh in our minds. So let's run this code. Here we go. Make sure I have room for it, and I hit the green arrow. I'm in Spider, and there's my, that's the editor in Anaconda, and there's my outcome. So yes, the length of a quadray is the same as from the center of this cube to any vertex. The body diagonal is square root of 3 times square root of 2 over 2, so half of that is what the length of the quadray is, and the distance across any 2 quadrays like A and B is what we were checking. That's going to be 1, so you see 0.99999. That's close enough. Floating point. And the IVM volume, there's what we were looking for. Again, floating point inaccuracies have creeped in at some point, but it's 0.25 basically, or 1/4, which is what we'd expect. The IVM volume is a little bit smaller. It takes a little bit fewer XYZ cubes to express the same amount because they're a little bigger. And the R cube is the result of 6 times the XYZ 1/6 of a cube that you get when you get that fragment. 1/8 of an octahedron taken out of a cube is actually 1/6 of that cube's volume. That's a useful thing to remember for future computations. So that's a good beginning. I recommend you head over to GitHub if you're interested in getting some of this Python downloaded and tested. You'll see that TetraVolume comes with lots of unit tests, and you can add some of your own just to confirm that things are working the way you expect. Currently, the tests are all passing, so I feel like conceptually this is ready for public release, and that's why I'm explaining how to use it. Have fun and let me know what you find out. Talk to you soon.